Section 10.5 Post-Tag Systems. Mathematician Emil Leon Post of the Courant Institute of New York University invented post-tag systems in 1928. The basic idea is very simple. You start with a string of bits, then you take some bits from the front of the string, replace them with a different set of bits, and put them on the end of the string. You keep doing this. One of three things will happen. Either the string shrinks until you can't do this anymore, or you get into an endless repeating cycle, or the string grows forever. Historical aside. Post did not create his post tags for use in cryptography. Post proved that the question of whether the string grows, shrinks, or repeats cannot be answered within standard mathematics. Then he used this fact to construct a proof of Kurt Gödel's famous incompleteness theorems. I consider this to be a simpler and more elegant proof than Alan Turing's proof using symbols written onto an infinite tape, although the similarity between Post's bit string and Turing's tape is striking. This Post substitution is similar to Huffman substitution, except that you move the substitute to the end of the bit string. The advantage of this system is that you can keep right on going after you have substituted for the entire string. That is, you can go through the string more than once. This obliterates the divisions between the Huffman codes. The pieces that you take from the front of the strings are called the tags. The set of tags must be chosen so that there is at most one tag that can be taken at each step. That is, the replacement process is deterministic. This requires that the set of tags has the prefix property. This will allow you to use the set of tags to encipher a message represented as a bit string. The prefix property is discussed in section 4.2.1 in connection with Huffman codes. In brief, no tag may begin with any other tag. For instance, you could not have both 1101 and 11011, because if the string started with 11011, you would not know whether to take the first 4 bits or the first 5 bits. With the prefix property, there is no need to have a separator between the tags, the way that Morse code groups need to be separated. The Huffman codes and Post tags have the same form, but they are used differently. For starters, Huffman codes are used to shorten the bit string, while Post tags are not. A method for constructing a set of Huffman codes is described in section 10.4. When you encipher using Post tags, you replace each tag with another tag and move the new tag to the end of the string. Since Reaver will have to decipher the message working from the right, the replacement tags will need to have the suffix property, that is, the inverse of the prefix property. None of the suffix tags can end with another suffix tag. For example, if 1011 is one of the suffix tags, then neither 01011 nor 11011 could be a suffix tag. You can construct the set of suffix tags the same way that you construct the set of prefix tags, except that you extend each tag on the left rather than on the right. If this is confusing, you can just construct a second set of prefix tags and then reverse the order of the bits in that set to get the suffix tags. There must be at least as many suffix tags as prefix tags. There can be more. The extra tags can be used as homophones. For example, the prefix tag 0111 might be replaced by a choice of suffix tag 110 or 10101. When the expected length of the suffixes is less than the expected length of the prefixes, the string is likely to shrink. That is, it is probable that there are some initial strings that will grow shorter. Conversely, if the suffixes are longer than the prefixes, it is probable that some initial strings will grow. This is usually true when homophones are used. The greater the difference in expected length, the more the initial strings will shrink or grow. However, probable is no guarantee. It is possible to construct prefix/suffix sets that have the opposite behavior. To use POST tags for encipherment, you first represent the message as a string of bits, then you perform the tag substitutions a few times. If you are enciphering by hand, you turn those bits back into characters. If you are enciphering by computer, this last step may be unnecessary. You simply transmit the resulting bit string. Section 10.5.1 Same length tags. One problem with the cipher described in the preceding section is that Riva does not know how to divide the message she receives into blocks. You might need to have a separate length field for each block, or else treat the entire message as a single block. This can be unwieldy when the message is long. One solution to this problem is to replace each prefix tag by a suffix tag of the same length. That way, the blocks stay the same length throughout the process, and there is no problem in demarcating the ends of the blocks. Block sizes of 32 bits or 64 bits are typical. I suggest doing a fixed number of substitutions for each block. You can determine the appropriate number from the shortest length and the expected length of the tags. Say the blocks are 32 bits, the shortest tag is 3 bits, and the expected tag length is 4.3 bits. Using the shortest length, if you perform at least 32 over 3 equals 10.67 substitutions, then you are guaranteed that every bit in the block is substituted at least once. Round that up to 11. Using the expected length, on average 32 over 4.3 equals 7.44 substitutions are needed, so that every bit gets substituted. A good margin of safety is to have each bit substituted twice on average. Double 7.44 and round up to get 15 substitution steps. This is greater than 11, so it is certain that every bit is substituted at least once. On average, every bit is substituted twice. About half the time, some of the bits are substituted 3 times. Most importantly, Emily will not know how many times any given bit has been substituted. You may have noticed that I have been saying every bit gets substituted rather than every tag gets substituted. This may be confusing. The first time through the block, each tag gets replaced with a new tag that has the same length. So, on the first round, it is the tags that get replaced. But when the second round of substitution begins, it might not start on an even tag boundary. That is, the next tag may span 2 or more of the tags from the first round. Here is a miniature example to illustrate the point using a 12-bit block. The first bit of the block is shaded, and the prefix tags are underlined. After 4 substitutions, the first bit is now in the second position, right in the center of the next prefix tag, which is 011. For hand use, I suggest encoding the letters of the alphabet as 5-bit or 6-bit groups, using 20 to 30 pairs of tags of 3 to 6 bits, 32-bit blocks, and 16 substitution steps, that is, about 2 times through the block. Convert the resulting bit strings back to characters using 4-bit groups to represent the letters A through P in some mixed order. Such a cipher would be rated 6. For computer use, I suggest using a standard 8-bit representation such as UTF-8 for the letters, digits and special characters in the message. Use 40 to 80 pairs of tags of 4 to 8 bits, 64-bit blocks and 32 substitution steps. Using 32 steps is enough for 3 passes through the block. Perform a well-mixed keyed substitution on the characters before doing the post tag substitutions, and a second independent keyed substitution on the resulting bytes after finishing the post tag substitutions. This cipher, called POST64, would be rated 10. It would have 4 separate keys used to mix the initial substitution, the final substitution, the POST tags, and their substitutes. Another way to use POST tag substitution is to use short overlapping blocks. Start with the first 4 bytes of the message and perform 2 POST substitutions. Assuming the tags are 4 to 8 bits each, this is sufficient to assure that all of the bits in the first byte have been substituted. Then move 1 byte right. The next 4-byte block of the message is bytes 2, 3, 4 and 5. Again, perform 2 POST substitutions on this block. Continue this way until the last 4-byte block of the message. The final 3 blocks will wrap around to the front of the message. This method, called POST OF, is rated 6.